Welcome back to the deep dive. Our mission today is highly specialized and deeply strategic. We are taking on the role of strategic consultants for a brand new university engineering team, and they're tackling the crucible of Formula Student Electric, or FSC.
Yeah, and this is a big one. This isn't just about building a fast car. It's a masterclass in project management under, extreme pressure.
Exactly. We've got their core blueprint, a guide called the Statement of Requirements, or SR, and it's written with this really rigorous, almost McKinsey-style approach. So our job is to distill this whole document into the absolute non-negotiable strategy for year one. They have to pass safety, they have to finish the race, or the project just, collapses.
Okay, let's unpack this.
And if we're going to guide a new team, we have to start with the core philosophy. It's a principle that comes from watching decades of success and, well, more often, failure in this competition. It's simple, but it gets missed all the time by students who are focused only on, raw performance.
Reliability defines the upper limit of your performance, but the architecture you choose determines the lower limit of risk you face.
Okay, that's a powerful statement.
It is. You can design the fastest car on paper, but if you can't finish that 22-kilometer endurance race, you get 0 points. The stakes are just astronomical. Our source material points to a terrifying stat. In top events like Formula Student Germany, FSG, over 40% of new EV teams, they either fail e-scrutineering, meaning they don't even get to turn a wheel, or they drop out of the endurance race.
40%. And what's the cause?
The failure mode is almost always related to thermal management or just basic high-voltage safety compliance.
So that 40% figure focused on heat and rules,
Yeah.
that tells me we need to stop thinking about peak power. We need to start thinking exclusively about what? Heat rejection and system integrity. Is that the starting point?
That is the only starting point. Speed is secondary to survivability. So how do we structure a project under that kind of intense risk? We borrow from the pros, aerospace, automotive. We use the systems engineering V model. This SRR uses that model as its backbone.
The V model.
We start with the high-level requirements, the specs. That's the left side of the V. Then you move down through architecture, subsystem development, and then you go up the right side of the V, which is all about rigorous validation, integration, and testing. That's where you prove that the system actually meets the requirements you set out at the beginning.
Right.
For a new team, adopting this structured approach is, it's their fastest path to building a system that's both competitive and, more importantly, verifiable and safe.
I appreciate the rigor, but doesn't the V model feel a bit bureaucratic? For a small student team that's already short on resources, it sounds like a lot of overhead.
It's not bureaucracy. It's risk mitigation. Think of it as a force structure. A new team's biggest enemy isn't the other teams. It's scope creep, unexpected failures, and no knowledge transfer when seniors graduate. The V model stops them from just diving into hardware design before they even know what they're building. It forces those early decisions to be tied directly to a test plan at the end. It saves months of rework.
Okay, that makes sense. You're building the test before you build the part. So let's move into that strategic context. The first step in any engineering project is defining your boundaries. And in FSE, that's the rule books. And we're not dealing with just one. There's FSG in Germany, FSAE in North America, FSEC in China. How does the team navigate that?
The rulebooks are the non-negotiable envelope, period. And while the trend everywhere is towards safety, efficiency, and intelligence, the emphasis in each region is, well, it's quite distinct. And that has to inform your design choices right from the start.
Okay, so let's break that down. FSG in Germany.
FSG is known for being extremely aggressive. It's the cutting-edge high-tech event. They're intensely focused on extreme efficiency, and they often allow wider wings, more complex aero packages. They're pushing the limits of downforce. And crucially, they're really accelerating the push into autonomous systems. They often make the DV, or driverless vehicle cup, mandatory. That forces you into a very specific kind of vehicle control unit architecture from day one.
So FSG is the high-tech aero-aggressive benchmark. What about FSLCE over in North America?
FSAE is historically more focused on mechanical simplicity, reliability, ease of maintenance. They tend to have stricter limits on things that generate ground effect, which keeps the cars more mechanically robust. They're less reliant on, high-cost, high-risk aero. So if you're building a car that needs to survive a lot of track time with few spares, the FSAE rules kind of gently guide you that way.
And FSEC in China seems unique. The outline mentions it's driven by China Manufacturing 2025. What does that mean in practice?
Exactly. FSEC has this incredibly strong industrial integration. So the competition leads to exceptionally high standards in things like energy density, control precision, manufacturability. The rules reflect that. You sometimes have mandatory sponsor logos from major players like NIO or CALB. It really underscores the push for real-world relevance.
Okay, so a team has to pick their target competition early, but regardless of those regional differences, the document points to this one hard unifying constraint: a voltage cap at 600 VDC and a max power output of 80 kilowatts. That's a great equalizer, isn't it?
It is the single most important strategic constraint of the entire electric class. You can't just outpower the competition. Everyone is capped at 80 kilowatts. So success hinges entirely on efficiency optimization and energy management. It changes the entire design calculus.
How so?
Well, think about it. You have to sustain that 80 kilowatts for the whole 22-kilometer endurance race. But if your inverter, your motor, your cooling system is only, say, 90% efficient, you're losing 8 kilowatts of power as pure heat. That wasted energy doesn't just slow you down. It stresses your thermal system, which, as we said, is the #1 reason new teams fail. The winning car isn't the one with the strongest motor on paper. It's the one that wastes the least energy.
And just to put 80 kilowatts in perspective for everyone, a basic electric sedan might have 150 kilowatters. A high-end one, over 400. We're talking about extreme power constraints relative to the car's weight here.
Correct. It means every single joule of energy, every watt of power, it all counts.
So let's look at the giants, the benchmarks. Teams like AMZ Racing or TU Delft, what are they doing at the limit, and why should a new team just not do that?
These teams are operating at the absolute technological extreme. AMZ uses 4WD in-wheel motors, custom-designed silicon carbide inverters, and extreme lightweighting to get their car mass below 180 kilograms. They hold the record for a sub-1.0 second 0 to 100 kilometer acceleration. That performance relies entirely on bespoke hardware and incredibly advanced software.
That sounds like what everyone should be aiming for, but for a new team, that sounds like a massive, massive risk.
It is the definition of a technology arms race, and new teams must strategically avoid it. The crucial insight for them is that their goal is not to beat AMZ in year one. Their goal is summed up by this Chinese phrase from the source material: finishing is winning. And that mandates a conservative, reliable, fundamentally sound architecture.
Trying to build a custom inverter in your first year is a guaranteed failure.
Guaranteed.
Okay, so let's nail down the concrete targets for this new team from the SOR. First, voltage, 400 to 600 volts. Why that range? Why push high?
Well, 600V is the hard ceiling. The reason to aim high, say 550V or 600V, is pure physics. It's about minimizing current. We have to keep coming back to the power loss equation. P loss equals I squared R. Higher voltage for the same power means lower current. And since loss is proportional to the square of the current, if you cut the current in half, you cut your losses by 75%.
And that has a knock-on effect.
A huge one. Lower current means you can use lighter, thinner cables for the HV harness. That's a significant weight saving right there. The trade-off is component availability. 400V parts are a bit easier to source, so that 400-600V range is the sweet spot.
Next, vehicle mass, under 240 kilograms. That still feels incredibly aggressive for a first-year car.
It is aggressive, but it's a non-negotiable strategic goal. New teams, they tend to over-design, be too cautious with structure, and they easily hit 280, even 300 kilograms. If you only aim for 260, you will overshoot. Setting a sub-240 kilogram target forces absolute discipline in every single subsystem.
And the performance target, under 4.0 seconds for the 0-75 meter acceleration. The top cars are sub 3.0. Aren't we capping their competitiveness?
It's a brilliant strategic compromise. That 4.0 second target is specifically competitive for a rear-wheel drive car. Chasing a sub-3.0's time requires 4 motors, 4 inverters, and a super complex torque vectoring brain. For a new team, focusing on 4.0 seconds lets them pour all their resources into making a reliable launch control for just 2 wheels. It's the most performance they can get reliably within their constraints.
Okay, that makes sense. Finally, battery capacity, 6.5 to 7.5 kilowatt hours. Why that specific number?
That's dictated by the energy needed for the 22-kilometer endurance race, plus a mandatory strategic margin. The rules basically force you to budget a non-negotiable 20% of buffer.
And that 20% isn't just for comfort, is it?
Not at all. It's critical. That margin accounts for real-world issues. First, cell aging. Your battery capacity degrades over the season. Second, cold temperatures. Cold battery on an early morning run performs way worse. And third, regenerative braking isn't 100% efficient. You don't get all the energy back. If you design for the bare minimum, you will run out of energy before the finish line.
So the 7.5 kilowatt target is really the survival capacity. It ensures they make it to the end.
Precisely. It's the reliability buffer built right into the spec.
Okay, let's move into the technical architecture itself, the drivetrain topology decision. The SOR says this is the single most critical choice they'll make.
It is. It defines the engineering path for the whole year. It commits you to a specific chassis, a specific mass distribution, specific cooling problems, get this wrong, and you're fighting the car's basic physics all year.
So let's break down the options. Option A, in-wheel motors or hub motors. This is what the top teams use.
Yeah, and the theoretical pros are very tempting. You get perfect independent torque vectoring, you eliminate drive shafts and diffs. But for a new team, the cons are overwhelming. I'd even say fatal. The key issue is a massive increase in non-sprung mass.
Remind us what non-sprung mass is and why it's so bad for handling.
Sure, non-sprung mass is everything not supported by the suspension. So the wheels, tires, brakes, and in this case, the heavy motor itself. When that mass increases, the suspension can't react fast enough to keep the tire in constant contact with the road over bumps. The wheel literally hops and skips. So you might have perfect torque control, but if the tire's in the air, that control is useless.
Okay, so poor grip. What else?
Well, hub motors need an extremely precise planetary gearbox inside the wheel hub. Manufacturing and maintaining that is very complex. And then you have the cooling and sealing challenge. The motor is right next to a hot brake disc. It's getting sprayed with water, hit with debris. It's just an extreme, high-risk engineering challenge.
So the conclusion holds, strongly discouraged for new teams, but shouldn't they be planning for it? Isn't RWD too cautious if they want to be world-class eventually?
It's a good question. RWD is cautious, but it's strategically necessary. Year one is about learning the rules and finishing the race. Every hour you spend trying to fix a leaky hub motor seal is an hour you're not spending on driver training or validating your safety circuits.
Which brings us to the recommended option B, inboard motors, mounted to the frame.
This is the sensible, low-risk choice. The main advantage is low non-sprung mass. Right away, your grip is better, your driver's more confident. Mechanically, it's way simpler. You're using a chain or gear drive. They're robust, they're proven. And crucially, cooling is straightforward. The motor is protected inside the chassis.
And the recommended architecture for year one.
A single motor RWD with a good mechanical limited slip differential and LSD. That keeps complexity to an absolute minimum. If they have a bit more resource, a dual motor RWD setup is a great compromise. Still low non-sprung mass, but it lets you start playing with basic software-based torque management. It's a great stepping stone.
Okay, now the make versus buy calculus. The SRR is emphatic about using commercial off-the-shelf, or COTS, parts.
COTS is the only way to go in year one. It mitigates risk, and it drastically shortens your development time. Every hour spent designing a custom part is an hour not spent testing the mandatory safety loop. It's a simple trade-off.
Let's talk specifics. The recommended E-motor, the MRAX 228 MV. Why is this the FSC standard?
It's the standard for a few reasons. Primarily, it's an axial flux motor. This design gives it a very high power density, so it's super lightweight, about 12 kilograms, and it's shaped like a pancake, which makes it easy to package in the chassis.
But there's a non-negotiable detail in the spec.
Yes, you absolutely must get the liquid-cooled version. The risk of heat soak during standing events, like the driver change in the middle of the endurance race, is just too high with air cooling. If that motor gets too hot while the car is stopped, the VCU will force it into a reduced power mode for the rest of the race, and that's a race killer.
That detail about heat buildup while standing still, that's a perfect example of thinking through the real-world race conditions. Okay, the inverter, the DTI FSAE or Cascadia PM100. This is where we get into silicon carbide. SiC MOSFETs.
Yes, and CC is the absolute future of power electronics. This is a strategic choice because it gives you a massive efficiency advantage under that 80 kilowatt cap. Compared to older silicon IGBTs, CC lets you switch at much higher frequencies, over 20 kilohertz.
And why is that high switching frequency so important in this 80 kilowatt limited world?
It boils down to reducing power loss. Every time a transistor switches to create the AC waveform, a tiny bit of energy is wasted as heat. With CCCO, you can switch more often, but the energy lost per switch is much, much smaller. Lower losses mean more of that precious 80 kilowatt actually makes it to the motor shaft, instead of just becoming waste heat that your cooling system has to deal with.
So it's a double win, more power and less heat.
Exactly. And the DTI-FC is a favorite because it's tiny, about 1.1 kilos, and it has a lot of the safety features like HVL support built right in. That saves a ton of time.
Finally, the transmission, a Drexler LSD. By going mechanical, aren't we giving up on fancy electronic traction control?
You are. And that is the right strategic trade-off for year one. Drexler is the industry standard. It gives you reliable, predictable mechanical grip. By using a solid mechanical solution, the team drastically reduces its dependency on building a complex, buggy electronic traction control system in their first year. They can focus their limited software time on mandatory safety stuff.
Okay, let's dive into the accumulator. Section 3. The SRR calls this the most dangerous and rules-constrained component. It sounds like this is less about performance and more about just survival.
You're absolutely right. The accumulator, or TSAC, is the single biggest safety risk and the biggest scrutineering hurdle. You fail here, the team goes home, period. For year one, the strategy has to be reliability over density.
Let's start with cell format. The recommendation is cylindrical cells, 18650s or 21700s. Why are these the reliable choice?
Because they have a steel case. That gives them inherent mechanical strength. They're standardized, they're tested to death, and their failure modes are very well understood. Even top teams like AMZ still use them for their robustness.
And what's the advantage of the newer 21700 format over the classic 1960?
The 21700 gives you more energy capacity per cell, which means you need fewer cells overall. But crucially, its larger size gives you more surface area for liquid cooling contact. That's vital for pulling heat out during the endurance event and keeping the cells below that 60°C safety limit.
But you hear a lot about pouch cells for their amazing energy density. Why are they such a risk for a new team?
Pouch cells offer the best density because they don't have that heavy steel case, but that also makes them mechanically fragile. The critical risk, though, is their physical behavior. They physically expand by 8 to 10% when you charge and discharge them.
Wait, they swell up by 10%? That's a lot.
It's a huge amount. And managing that expansion is an incredibly complex engineering problem. You need a special module design that applies pressure to the cell, but also allows it to expand without breaking the container or the seals. For a new team, getting that right is a huge, unnecessary risk.
So cylindrical is the way to go. Now, the fortress around them. Structural integrity. The rules for the container sound extreme.
They are. EV 5.5 requires the container to withstand 40 grams of force, sideways and forwards, and 20 grams vertically. We need to really understand what that means. For a 50-kilogram battery pack, the mounting points have to resist 20,000 newtons of force. That's like holding up 2 metric tons.
So what materials do you use to do that without breaking the bank on certification?
Steel or aluminum alloys. It's a simple choice. Why? Because proving their strength, the structural equivalency, is straightforward math you can show to the scrutineers. Carbon fiber, CFRP, is the risky one. If you use carbon, the rules often demand you physically destroy samples in testing to prove they're strong enough. That costs a fortune and takes months. A new team can't afford that.
Okay, beyond just strength, there's fire safety, thermal runaway.
Right. All materials inside the battery box have to meet a UL 94V0 fire rating. But the core rule is about containment. You have to prevent a fire from spreading for at least 5 minutes to give the driver time to get out. That means using substantial thermal barriers like 6mm thick plates or specialized materials like pyrethin that can withstand over 850 degrees Celsius.
And there's a specific electrical rule if you use composites, the Faraday cage.
Yes, that's mandatory. Carbon fiber isn't electrically conductive, so there's a risk of a high voltage arc if a terminal touches the wall. So if you use a CFRP container, you have to line the inside with a grounded aluminum foil or mesh. It creates a Faraday cage and prevents that arcing and fire risk.
Let's talk about the brain of the battery, the BMS, and thermal monitoring.
The rules are getting tighter every year. FSG 2025 mandates monitoring at least 30% of all cells, and the key action is the trip point. The BMS must trigger a full shutdown if any single sensor goes above 60 degrees Celsius. That's a hard limit.
And what's the crucial functional safety requirement for the BMS and the relays? It's a fail-safe principle, right?
Yeah. It is. The BMS must control the main high-voltage relays, the ARERs, directly, with a hardware connection. It is absolutely forbidden to just request a shutdown over the CAN bus, because if the CAN bus crashes, the relays must still open. Hardware control guarantees it no matter what the software is doing.
And for advanced testing?
The BMS needs to support real-time telemetry, 4G or radio. This lets the team watch for temperature imbalances across the pack during testing. And critically, they can track the internal resistance of the cells. That's how you predict how much life the pack really has left.
All right, we've reached the section on scrutineering killers. These are the things that if you get them wrong, you're guaranteed to go home early. This is what separates you from that 40% failure rate.
Absolutely. Performance means nothing if you can't pass the electrical safety inspection. This is all about eliminating single points of failure.
Let's start with the IMD, the insulation monitoring device, the watchdog.
This is mandatory hardware. The standard is the Bender IR155. Its job is to constantly monitor the insulation resistance between the high-voltage bus and the car's chassis ground.
And what's the threshold it's looking for?
The rule is $500 omega V sita. So for a 600 V system, if the resistance drops below $300 of omega, it has to trigger a latching fault and shut everything down. That threshold is designed to keep any potential leakage current well below a dangerous level, especially if water gets in.
And the integration is critical.
Vital. The I&D status output has to be hardwired directly into the shutdown circuit. Again, no software in the critical path.
Okay, second major safety device. The brake system plausibility device, or BSPD. This prevents simultaneous braking and acceleration.
Exactly, it's there to stop a runaway car, which could be caused by a stuck sensor or a software bug.
And the most surprising rule here is that the BSPD must be a non-programmable circuit. Why are they forcing students back to old-school analog electronics?
It's a hard rule, born from past incidents. It prevents a software bug from causing a disaster. You can't use a microcontroller. It has to be built with analog op-amps like an LM393, or discrete logic gates. The trigger is very specific. If brake pressure is over 30, bar A&D motor power is over 5 kilowatt for more than 500 milliseconds, it cuts power. Scrutineers will literally hook up single generator to your car to test that 500 millisecond delay. If you're off, you fail.
So the nerve center holding all this together is the shutdown circuit, the SDC.
The SDC is a physical, hardwired series circuit. It's like a chain of tripwires. This chain controls the power to the main high-voltage relays. If any link in that chain breaks, the relays snap open and the high voltage is cut instantly.
And what are the links in that chain? The SRR lists 6 types.
6 categories, yeah. You have the 2 master switches, you have 3 big red emergency stop buttons around the car, you have an inertia switch that trips in a crash, a brake over travel switch if the pedal jams, the high voltage interlock loop, the HVIL, which makes sure all connectors are seated, and finally, the hardwired fault outputs from the BMS and the IMD. Every single one has to be in that chain.
That sounds like the ultimate defense layer. Okay, let's talk power flow. Pre-charge, discharge, and wiring. What's pre-charge?
Pre-charge is critical for protecting your hardware. Before you close the main relays, a smaller circuit with a resistor has to gently charge up the big capacitors in your inverter to about 95% of the battery voltage.
And what happens if you skip that step?
A catastrophe. It's called inrush current. You get this massive surge of amps that can literally weld the contacts of your relays shut. If the relays are welded shut, you can't open the high voltage circuit anymore. The car can't be made safe. It's a fatal failure.
Then after a shutdown, you need active discharge.
Correct. The rules say the high voltage bus has to drop below 60 volts within 5 seconds. The inverter has its own discharge circuit, but it's often not fast enough. So teams usually need to build a dedicated circuit with big resistors to bleed that energy off quickly to pass the test. If it takes 5.1 seconds, you fail.
And finally, wiring. This seems basic, but the rules are strict.
They are non-negotiable details.
Yeah.
All HV cables must be safety orange, no exceptions. And they must have 360-degree metal shielding, which has to be grounded. That shielding stops electromagnetic interference, EMI, from messing with your sensors or your CAN bus. And all your connectors have to be IP67 rated, touch-proof, and include those HVIL loops. Good wiring is good safety.
So this whole safety system, IMD, BSPD, SDC, it's a complex, layered system of physical tripwires. It ensures that no matter how badly the software fails, the car can never hurt anyone. It's safety by redundant physics.
That is a perfect summary.
All right, let's shift from the hard physics of safety to the soft power of software. Section 5, the Vehicle Control Unit, or VCU, the brain of the car.
The VCU choice is a defining moment for a team. It dictates how fast you can develop and iterate. We recommend professional, real-time hardware. Things like a D-Space micro auto box, or high-performance embedded boards like a Teensy 4.1 or an STM32H7.
And what's the big don't here? What does the SRR explicitly ban?
It's explicit. Ban Raspberry Pi or Arduino as your main vehicle controller. Why? Because they run a non-real-time operating system. You can't guarantee that a critical command like reading the throttle and sending a torque request will happen in a predictable time frame. That lack of deterministic timing is unacceptable for vehicle control and safety.
On the software side, the recommendation is model-based design, or MBD. Why is that better than just hand-coding everything?
MBD, using tools like MATLAB and Simulink, is the industry standard for a reason. It forces clarity, it simplifies validation, and for a student team with high turnover, it ensures knowledge transfer. The next student doesn't have to decipher thousands of lines of C code. They have a visual functional model that generates the code. They can get up to speed much faster.
Okay, let's talk about the communication backbone, the CN bus strategy.
This is the difference between smooth sailing and total chaos. From day one, the team has to define a unified DVC file, a database for all the CN messages. If you don't have a central dictionary for your data, you'll waste weeks just trying to debug which sensor is sending what.
And you need to structure the network itself.
It has to be segmented.
Yeah.
Two separate physical CAN networks. CAN 1, Powertrain, is for high-priority stuff, VCU, inverter, BMS. Its bandwidth usage, the load factor, has to be kept below 60% to guarantee messages get through on time. CAN 2, chassis log, is for everything else. Dashboard, data loggers, sensors. This separation ensures a flood of data logging doesn't choke out a critical torque command.
Moving to performance software, basic torque control. How do you map the driver's foot on the pedal to the motor's output?
It should never be linear. You want a nonlinear map. So less sensitive at the beginning of the pedal travel. This gives the driver really fine control in slow corners or in the pits. It prevents that jerky on-off feeling and helps preserve grip. Then, once you push past maybe 70%, the curve gets much more aggressive for max power.
Then there's regenerative braking, RBS. This isn't just a gimmick, it's critical for the efficiency score.
RBS is an absolute necessity. A good system can recover 20 to 30% of your energy. That's huge for your score. The strategy you need is called decoupled braking allocation.
What does that mean in control terms?
It means the system prioritizes braking with the motor first, the regenerative braking. It only starts blending in the mechanical friction brakes when the driver asks for really heavy braking. So the total braking is always a sum of regen torque and mechanical torque. It's a complex control problem.
And the BMS has to have veto power over this, right?
Absolutely. The BMS must stop regenerative braking if the battery's too full, say above 95% state of charge. You can't force charge into a full battery. It also has to veto it if the battery's too cold, because cold cells can't accept charge quickly. And the VCU software has to be smart enough to prevent rear-wheel lockup. As you brake, weight shifts forward, so if you regen too hard on the rear, the wheels will lock.
Finally, the future path. Torque vectoring, or TV. Even though they're starting RWD, the blueprint says the software needs to be ready for it. Why?
Strategic foresight. Scalability. The RWD car is a learning platform, but your software architecture can't be a dead end. TV is all about actively managing the yaw moment of the car by varying the torque to the left and right wheels.
So even in year one, they should be modeling this.
Yes. They should be working with the core math, the 2-degree of freedom single bike model, which calculates the ideal yaw rate for a given corner. The VCU's job is then to adjust the wheel torques to achieve that ideal yaw rate. It makes the car turn sharper than the tires alone would allow.
So they're building the intellectual foundation for what comes next.
Precisely. The advanced path uses things like Kalman filters to estimate tire conditions. That software intelligence is what ultimately separates the top teams from everyone else. The true competitive edge is in the code.
Okay, we've defined the strategy, designed the parts and the software. Now, V-model implementation, validation and testing. The source material says 70% of success is found right here. This is the difference between a pretty CAD model and a functional race car. Here's where it gets really interesting.
This is where most new teams fall down. They spend 9 months designing and 1 month testing. It should be the other way around. The V model forces you to plan your tests from day one. Every requirement on the left side of the V has to map to a validation step on the right.
Let's start on the left side, design verification.
You have to take a high-level target, like that under 4 seconds acceleration, and break it down into verifiable specs. So that means the motor must produce over 200 newton meters of torque, which means the battery must be able to sustain over 200 amps of discharge current. Everything has to be traceable.
And the simulation phase, model in the loop or mill it.
Mill-L is your crystal ball. You use a full vehicle model in something like Simulink. You can run virtual laps of the Hockenheim track to figure out your optimal gear ratio and, critically, predict the thermal loads on your battery and motor. This stops you from building a gearbox with the wrong ratio or a cooling system that's totally undersized.
Now we cross the V to validation. First up is hardware in the loop, or HIL. This is the bridge between simulation and reality, and it's designed to stop you from blowing up expensive parts.
HIL is the most important risk mitigation step you can take. You connect your VCU not to the real car, but to a simulator that pretends to be the car. It sends all the sensor signals, motor current, brake pressure, and you can simulate faults. You can tell it to simulate an over-temperature event or a CAN bus failure.
So you're basically giving the VCU's brain a flight simulator to test its survival instincts.
Exactly. You're testing the full handling logic safely. Does it do the right thing when the simulated BMS screams 61 degrees? After hill, you do dyno testing. Put the real motor and inverter on a dynamometer and validate your efficiency maps in your cooling loop under full 80 kilowatt load.
And then the real world, field testing.
A minimum of 100 kilometers on a real track. Mandatory.
Yeah.
But the ultimate test for the electrical system is the rain test.
The rain test sounds like a nightmare. What are the conditions?
It is the single hardest test for electrical integrity. The car has to sit high voltage active for 2 minutes while being sprayed with pressurized water. Then 2 more minutes after the spray stops, all without the IMD tripping. It tests every seal, every connector, every single design choice related to water ingress.
What are the common failure points?
A poor seal on the battery box is the obvious one, but a subtle one is the cooling fans. If they're aimed poorly, they can actually suck water mist into your high voltage connectors, causing a short that trips the IMD.
And the final step is data acquisition, or DAQ, closing the loop.
You need high-frequency loggers that sync everything. GPS, motor current, cell voltages, yaw rate. This lets you do a virtual-to-real comparison. You take the real track data and you feed it back into your simulation model to see where they differ. That's how you really optimize your control algorithms.
Before we leave this, what about the common physical mistakes, the stupid failures that get you sent back from scrutineering?
Oh, there are classics. Number 1, lack of positive locking on fasteners. Every critical bolt needs a nylock nut or safety wire. Thread locker isn't enough. Number 2, terrible wiring. High voltage and low voltage wires have to be physically separated and properly secured. And number 3, the one that always surprises teams, driver egress. The driver has to get out of the car in under 5 seconds. If your battery box is in the way, you fail.
Okay, let's step back into that strategic consultant role. Project management and finance. Great engineering doesn't mean much without a budget and a team to support it.
Absolutely. The estimated year 1 budget, not including travel, is around $35,000 USD. And critically, the team has to hold a mandatory 15% contingency reserve. Something will go wrong. A part will be delayed. A component will fail. Without that buffer, the project grinds to a halt.
And where's the bulk of that money going? It sounds like it's mostly being spent on risk mitigation.
Precisely. The goal is reliability through proven parts. The key cost drivers are the motor and inverter, which can be $10,000 to $14,000 for a good COTS setup. Then the battery cells, BMS, and fire retardant materials are another $6,000 to $8,000. These are the big ticket items you buy first.
On team structure, the SRR mandates a specific role, an electrical safety officer, or ES.
This is non-negotiable. The ESO's only job is to find flaws. Their job is to act like the meanest scrutineer you can imagine. They check every safety design, every document, every wire, and they must have veto power over safety designs. It creates a necessary tension between the design team and the compliance team.
Let's talk about the static events. The cost report is worth 100 points, but it's not just about adding up receipts.
Not at all. It's a manufacturing analysis. You're trying to prove your car could be produced cheaply. Scoring high is all about strategic design for manufacturability, DFM.
Give us a concrete example of that.
Okay, say you designed a fancy suspension upright that needs a 5-axis CNC machine. That's a huge virtual cost. Strategically, you might replace it with 2 simpler parts made on a 2.5-axis machine that you then weld together. The physical part might be a tiny bit heavier, but your virtual manufacturing cost in the report plummets and your score skyrockets.
And finally, documentation, the ESF and SES.
Documentation is your team's professional face. You have to maintain a detailed bill of materials from day 1 down to every screw. High-quality professional documents give the judges a good first impression, which is vital for the subjective design finals. Bad paperwork just invites them to dig deeper for problems.
Okay, so if we tie this all together,
If we connect this whole blueprint to the bigger picture, the journey for this team has to always come back to system integration and, above all, reliability. We spent most of our time talking about safety, hardware, and compliance because that is the foundation performance is built on.
right.
If you don't pass scrutineering and you don't finish endurance, everything else, your fast acceleration, your fancy inverter, it's all just academic. The philosophy holds. A slightly heavy car that finishes is strategically better than a lightweight marvel broken in the pits.
So let's summarize the final takeaways, the 4 pillars of success.
First, reliability. Finishing is winning. A heavy car that crosses the line beats a light one that doesn't. Second, compliance. The rules are the red line. Empower your ESO to make sure you never cross it. Third, testing. You have to budget at least 3 months for structured testing. A race car should show off proven results, not debut new systems. And fourth, safety culture. Treat every safety system, the IMD, the BSPD, the SDC, as your team's absolute last line of defense.
We've covered a dizzying amount of detail today. from 40 shear forces to the need for analog op-amps in the BSPD. It's clear that in modern FSE, the line between success and failure is drawn in the control code and the compliance document, not just in the metal.
The complexity has absolutely migrated from the mechanical world to the electrical and software world.
So what does this all mean? The most complex challenge in FSC today isn't the mechanical design. It's mastering the soft power of software, that MOS TV component, the torque vectoring algorithms. We've seen this shift from relying on mechanical reliability, like a Drexler LSD, to relying on software control. So the provocative thought I'll leave you with is this. Which dependency is riskier for the future of racing? The mechanical reliability of a physical part engineered to withstand a known 40 green load, or the stability of software logic derived from complex, real-time equations that's managing the car's stability at the very limit of adhesion. That's the ultimate engineering challenge ahead.
A question that really defines the next generation of Formula student. Mastering that software stability is the key.
Thank you for joining us for the deep dive. We hope this blueprint gives you the knowledge to start thinking like a world-class Formula student strategic engineer. We'll catch you next time.